Okay students, welcome back. So, in the last lecture I have given you a problem based on a spirocyclic compound, and I said this is one of the intermediate for a natural product which is isolated from a South American frog. Now, if you see the retro which was discussed in the last lecture, we come back to this Beckmann rearrangement transformation, and we said Beckmann rearrangement is basically a transformation where a cyclic hydroxylamine or cyclic oxime basically undergo a ring expansion reaction to go to the higher ring. So, if you have a 5-member oxime that will undergo a ring expansion to give you a 6-member amide, fine. So, now how you can make this oxime? Next will be the very interesting reaction which probably we need to spend some time. We have a OH here, we have a N-butyl here. Now, if I draw a intermediate something like this, you say that this left hand ring is absolutely unfunctionalized, then how you are planning to introduce a oxime or a keto group into this? I said that here there are OS, and this is a very interesting reaction, is alpha, beta, gamma, delta. Now, this particular reaction or this particular transformation is basically named as Barton nitrile ester photolysis. This will be explaining nitrile ester photolysis, what exactly this reaction is and how it takes place. Now, Barton nitrile ester photolysis was first invented by Sir Derek Barton, who got the Nobel Prize in chemistry working on the conformational aspects of several steroid molecules. Now, if you see it, this reaction is basically a remote functionalization of a molecule. Now, here I said that is alpha, beta, gamma, delta is a delta functionalization, and nitrile ester means that you need to have a nitrile ester of the corresponding alcohol. So, now try to analyze what is the Barton nitrile ester photolysis. So, we will be explaining what is Barton nitrile ester. Okay. So, we will be having a starting material alcohol something like this, and now we say if you analyze the alcohol is a alpha, beta, gamma, this hydrogen is delta. So, initially what was done, if you have this kind of alcohol, you react with NOCl, nitrosyl chloride. So, nitrosyl chloride will basically react with this alcohol to give you a nitrile ester. That is why it is called Barton nitrile ester photolysis. As the name implies, photolysis means somewhere you have to use a photon source or light source. Now, this light will basically give you a heterolytic cleavage of this O nitrogen bond. So, once this thing takes place, you will basically have the O dot, and actually this is going by this way and is a half arrow, and you get a O dot and you basically get a NO dot. So, this heterolytic oxygen nitrogen bond is cleaving, okay. And then this oxygen dot now abstracts the delta hydrogen alpha, beta, gamma, delta through a 6-member transition state. So, 1, 2, 3, 4, 5, 6 a closed transition state, and once it abstracts it, this O now become OH, and then it puts a radical here. Now, this NO radical is sitting idle, okay. So, NO radical is basically here. So, what it does, this radical are repairing. pairing, radical radical pairing, and once this radical radical pairing takes place, will be, this is now OH and this will be now having this NO. Okay. After this radical radical pairing. Now, this compound is having again a hydrogen, and this is kind of a tautomerization will takes place to basically give you the corresponding oxime. So, this is in the nutshell the Barton nitrile ester for photolysis. The key features is a remote functionalization, the remote CH functionalization, and this is very important reaction. This is done by light, and normally delta hydrogen abstraction takes place. So, now you try to fit it in this our model. We will be now doing it. So, next, if you apply this Barton nitrile ester photolysis, the intermediate which you have earlier figured it out, is basically you are having a N-butyl, you are having a OH here. So, we will put a nitrosyl group here, ONO, then this is alpha, beta, gamma, delta. Now, eventually you are having, if you go back this way, you are having alpha, beta, gamma, delta, this is also another delta. Now, as I said, this molecule has a unique stereochemistry, so we did not discuss it to make your life simpler. In reality, you will find that only this delta hydrogen is in close proximity with this OH, because the 3-dimensional structure we did not consider. Fine. So, now this compound you have to prepare. This compound basically you can prepare by simple functional group addition by a functional group interconversion through a hydroboration chemistry. Hydroboration simply all of you know, very standard hydroboration chemistry. Okay. And then the chemistry which was, or the retro which was drawn here, probably all of you know. This intermediate we have discussed in the retro quiz, try to remember. So, this is basically will be coming from a pinnacle type of rearrangement which we all discussed previously, and this compound is a pinnacle rearrangement transformation, and this one it is simple coupling of two equivalent of cyclopentanone. So, we are now trying to come back to the original starting material which is cyclopentanone. It was very cheap. The cyclopentanone starting material was not given to you, but the point is, until and unless you know the Barton nitrile ester photolysis, the whole pathway is impossible for you to design. Okay. So, next what we will do, we will try to go back to the forward pathway. Starting material is this, you do the initial magnesium mediated coupling, this is very simple. So, no, we will do a pinnacle rearrangement, and that will basically give you the spirocycle thing. Okay. Then you do a N-butyl lithium reaction here, that basically give you a addition of OH and N-butyl nucleophilic addition, you make corresponding methyl chloride by treating this alcohol with methyl chloride and do a 1,2 elimination, that basically give you the corresponding olefin which is required. Okay. Then you do the hydroboration by boron THF. So, this hydroboration will then give it to this compound. So, this compound now you react with nitrosyl chloride and shine light. So, nitrosyl chloride and light will basically give you the intermediate O N double bond O. N butyl is here, you draw the spirocycle remaining part. Now, I say is the intermediate, okay, and then you do the Barton's reaction, nitrile ester photolysis. So, alpha, beta, gamma, delta, the oxime will come here. So, what basically you will get? You will basically get OH here, N butyl, and this side cyclopentane ring will be now having the oxime, and then you do a Beckmann rearrangement, based transformation, that is also very standard reaction. And your N butyl will be remain here. Now, here you will basically get the ring expanded thing, you will get the ring expanded thing. Now, normally Beckmann rearrangement is basically migration towards electron deficient nitrogen. Now, more stabilized or more substituted carbon will basically migrate. Now, out of these things, basically there is a possibility either this carbon can migrate, this carbon can migrate. Now, this carbon is more substituted. So, this will migrate, and that is why this carbon is having direct nitrogen bond. Okay. So, once Beckmann rearrangement is done, your next job is very simple. You now try to correlate the final target structure. You are having here N butyl, and then is a NH double bond O. You are doing a reaction with lithium aluminum hydride, as I said, reductive cleavage, not cleavage, reductive transformation, and then you basically get the amide NH. So, this is your final target, try to remember. So, the silent features of the whole synthesis was couple of interesting reaction we talked about, but definitely the key transformation is the Barton's or Barton nitrile ester photolysis. It is absolutely brilliant reaction, nitrile ester photolysis, that was the main key reaction, key transformation, the remote delta CH functionalization through a photochemistry, okay, photochemical pathway. In addition, you are also doing couple of interesting transformation. The key is Beckmann. The Beckmann reaction or Beckmann rearrangement was used in the final stage, and then pinacol-pinacol rearrangement, which was very crucial, was used, and then you do couple of functional group interconversion or functional group addition. So, your main synthesis is basically combination of all those things, but as I said, if you are not familiar with this Barton nitrile ester photolysis, it is very difficult to design the entire pathway. Beckmann rearrangement and other things are basically coming into picture at a later stage. So, this will basically give you the how different powerful transformation can be applied in a sequential manner to give you a complex or medium complex size molecule. Next we will draw a target, but eventually this case we will not discuss the forward path. We will just say this molecule can be constructed through this pathway and what are the possible transformations you can think about. If there is a new transformation, we will definitely discussing this transformation. Now, as I said, the stereochemistry was not discussed. This is a natural product, it is basically a stone hormone, and now this compound was synthesized long ago. Okay. Now, we are trying to use multiple transformation based strategies, how multiple transformation is combined together to give you a target molecule which is desired by you. Now, for this molecule you see that how we disconnect the molecule. In the very beginning the disconnection looks very complex probably. It gives you a 5-member ring at this right end and then you put a cyclobutane ring fused with a benzene ring. Now, definitely this was very judiciously or very cleverly done, means that there might be some transformation available. Now, what can be thought of? The idea was basically the central cyclohexane ring can be devised through a Diels-Alder kind of transformation. Now, eventually it is very difficult to assume at this stage. Now, if we have this kind of intermediate which is basically named as benzocyclobutane. Now, benzocyclobutane under thermal condition will basically undergo electrocyclic ring opening to give you this intermediate, which is nothing. This is benzocyclobutane. This basically give you intermediate whose name is orthoquinodimethyde. Now, these orthoquinodimethydes are powerful diene. If you have a suitable dienophiles, it immediately undergoes ring closing things, because the final left side ring is getting the aromaticity. So, benzocyclobutanes in principle the structures will be something like this, and basically this part you can think about a 4 pi electrocyclic ring opening, that basically gives you the benzocyclobutane. Now, as I said, it is very easy to write in the paper, okay, but when you in reality you do the practice, then so okay, come back to the intermediate which you have earlier drawn based on the benzocyclobutane and orthoquinone dimethyde chemistry. You see the right hand part remains similar. Okay. So, now we say that this compound you can basically visualize from a this type of primary iodospecious and this cyclopentenone as a Michael acceptor, as well as we will be using a vinylic copper lithium as a Gilman reagent. Now, how this reaction takes place? It is basically 3 component reaction all together. This is a Michael acceptor, there is a nucleophile vinylic copper lithium. So, first case this 1,4 addition takes place. So, once this 1,4 addition take place, you basically have this vinyl group here. Now, this double bond basically shifted, or the anion has been shifted. So, initial nucleophile species come here, this electron has been shifted, the anion has been relayed from here to there. This will be explaining when you talk about anion relay chemistry. Fine. Now, this is basically a enolate. So, this enolate come back, puts the negative charge here. Okay. And this is now going to be trapped by this electrophile, which is here. So, we will basically get the electrophile, and all the things will now react in a your cyclopentanone, these things. So, yeah, obviously your methyl is there, another methyl is there. So, you are having a methyl here. So, you are having a methyl here. Okay. So, now see, this is the vinyl, this is the vinyl, this is the vinyl. So, this is now same, these two compounds are now same. So, only thing is now you need to heat it, you just need to heat it. So, once you heat it, we will again write it down in the next slide how the final reaction takes place. So, this is your benzocyclobutane, we write it in this way. Okay. This is the methyl, this is the fine. Now, this vinyl group was basically appendate, acting as a appendage, and latter part this is serving as a dienophile in the real cellular reaction. So, next your thermal, as I say, 4 pi electrocyclic ring opening takes place to give you the orthoquino dimethyl structure. Your methyl. Now, see, two rings basically we are making together. If you see the target molecule is having this structure. Okay. So, there are 3 rings, 4 rings together actually. The left hand side is the benzene ring, we can call this is ring 1, this is 2, and this 3 ring is coming from the cyclopentanone, which is used as the starting material. So, ring 1 and 2. So, this part aromatic part is here, and this is the ring 3 or the cyclopentene ring, which came from the starting material. Now, this ring 1 and this ring 2, how it has been now coming? This is the diene part, this and this. So, 4 plus 2, once it close, it gives you 2 ring together. So, that was the very interesting. So, 4 plus 2 or dual cellular transformation takes place, and then basically you get the first ring 1, the second ring is this, and then finally you will be having the other ring. So, all together this is 1, 2, 3, your methoxy remains as it is, remain as it is. So, transformation wise, this synthesis of this estrone as a target molecule is simple, definitely very simple, and then but the only thing is you need to know exactly what is happening here. The transformation what we use here is basically a combination of a pericyclic reaction. Pericyclic reaction probably you have to study, because in the retrosynthetic pathway we are not going to talk about more of the reaction, because we have a restricted time. So, we use a electrocyclic ring opening, as well as we use a 4 plus 2 cycloaddition reaction, cycloaddition reaction. And then at the end we basically use this 4 plus 2 cycloaddition reaction. The beginning what we use? We basically use a 1,4 Michael addition with a properly substituted Gilman reagent. So, 1,4 addition or Michael addition type of reaction with enolate alkylation. So, all this proper combination of this different reaction making this whole process very useful and very successful. So, now if you see the target molecule which was the estrone part, which was the estrone or the real target molecule. Now, again go back to the retro, as I said, this retro is basically very simplified retro. We designed a 4 plus 2 cycloaddition reaction, but if you know that benzocyclobutane, this kind of compounds opens up to give the orthoquinodimethyl, then your job is quite easier. Until unless you know this transformation, you will be probably having tough time to formulate the entire pathway. Now, once this benzocyclobutane has been chosen as an intermediate, your next step is basically you think of using this as a electrophile. And the starting material is 2-methyl cyclohexenone, which is very cheap, and you react with a vinyl copper lithium, is a vinyl Gilman reagent. So, it is basically 1,4 addition of this vinyl Gilman in a Michael fashion, and then this electron basically undergoing rejuvenating things to put a enolate anion. This enolate now undergo enolate alkylation with this electrophile. Now, this electrophile once it attacks is basically a 3 component reaction together, 1 component, 2 component, 3 component. Sometimes this reaction is termed as multi component reaction. So, now you are basically here. Now, once you are here, then basically your 2 cascade pericyclic reaction, we call 2 cascade pericyclic reaction. 2 cascade means one after another, 2 cascade pericyclic reaction. As I said, pericyclic reactions we are not discussing in detail here. The pericyclic reaction which we are talked about here is a electrocyclic reaction, electrocyclic ring opening of this benzocyclobutane and a Diels-Alder cycloaddition. So, these 2 reaction is a key transformation which was used as the penultimate stage or the final stage, and in the very beginning we use this multi component reaction to access the core intermediate. So, we will try to continue our discussion based on this topic, as I said, and so try to analyze all the problems which was discussed till today. Try to go to any standard textbook, try to take the help of this internet, scene archive website, and just try to accumulate as much knowledge as you can, and then we will catch you in the next lecture. So, till then, goodbye.